Today what we're going to talk about is measures of position. We've already talked about measures of central tendency and measures of variation. What we're going to look at today is measures of position. These are used to locate the relative position of a data value in a set, and when we're talking about the relative position, we're talking about where is it that data point located in the data set in relationship to the other data points. Not just its number value or anything of that nature, but in relationship to the other data points. Like we know that the mean is usually a measure of the middle. Well, even that, we need to be able to compare. We need to be able to look at that measure of position. The first type that we're going to look at is what we consider the standard score, or the z-scores. These z-scores tell us how many standard deviations a data value is above or below the mean for a specific distribution. Just like when we were looking at the empirical data or the empirical rule before, where we were looking at whether we were one standard deviation away from the mean or two standard deviations away from the mean. This helps us look at how many standard deviations are we away from the mean for each data value. The standard z-scores also allow for comparisons. When we're talking about the z-scores, we have a formula, and it's the z is equal to the value minus the mean divided by the standard deviation. So the value minus the mean divided by the standard deviation. And again, whenever I do the formulas, it looks a little bit differently for the sample and for the population, just because of the variables that I use, the symbols that I use, but we calculate them in the exact same way. So for a sample, we have that the z is equal to the x minus x bar, which is the sample mean, divided by the s, which is the sample standard deviation. Whereas when we look at population, we have z is equal to our value minus the mu, which is our population mean, divided by the sigma, which is our population standard deviation. We calculate them in the exact same way. It just depends on, are we looking at the sample or are we looking at the population, as to what symbols we're using. Now then, the z-scores we're going to be using a lot throughout the semester, so we definitely need to make sure that we know how to use them. So let's look at an example. And we see here that we have a student scored 65 on a calculus test that had a mean of 50 and a standard deviation of 10. She scored a 30 on a history test with a mean of 25 and a standard deviation of 5. Okay, just looking at these, it looks like she did better in the calculus than she did in the history, simply because it's a higher score. But we always want to check things like that, because the relative position may not be the same, because we also have to think about, were they looking at a 100-point scale, or was it the 30 on the history test only out of a 50-point scale? Things of that nature. And so we want to look at those means and the standard deviation so that we can compare, did she do better than the rest of her class in the calculus or in the history class? So we want to compare her relative position. Is she in the higher position in her calculus or in her history class? So let's look at this. And let's do the calculus. And so her z, her score, this is going to be her x, this is her x bar, and this is her s, her standard deviation. So her z is 65 minus 50 divided by 10. So her z-score becomes 15 divided by 10, which becomes a 1.5. So in calculus, she has a z-score of 1.5. Let's look at her history class. So in history, her 30, her actual score, is her value. The mean is her x bar, and the standard deviation is her s. So we have that her z-score is going to be 30 minus 25 divided by 5. So 30 minus 25 is 5 divided by 5. So her z-score in her history class is, oh, not 5. It should be a 1. So what this tells us is that in calculus, she is 1.5 standard deviations above the mean. In history, she is only 1 standard deviation above the mean. So if I were to draw this on a line, if this is the mean for either one, for anything, if we think about a z-score, anytime I compare things and change everything to a z, it means that my mean is always going to become a 0. Anytime I change things to z-scores, the mean always becomes 0. And my standard deviation always becomes a 1. But if I look at this, the z-score for my the calculus class is a 1.5. The z-score for the history class is a 1. So notice that she has a higher position in her calculus class than she does in her history class. Okay? You're definitely going to need to know how to calculate the z-scores and things of that nature. Now, as I said, when all the data for a variable is transformed into z-scores, it changes everything, and the z values have a mean of 0 and a standard deviation of 1. So we've normalized it. We've changed everything so that our standard deviation is 1 unit and our mean is always 0, that center spot. So when we look at it on a number line, here's 0, and if I take my mean plus 1 standard deviation, that's going to be 0 plus 1, which is 1. And my mean plus 2 standard deviations, that's 0 plus 2 times 1, which is going to give me 2. Or the mean minus 1 standard deviation, that's going to give me a negative 1. And I could go both directions. These are for z-scores. So z-scores are positive and negative, and they usually range between about a 4 and a negative 4. They can go larger or smaller, but most of the time we try to keep them between a positive 4 and a negative 4. Okay? The second type of relative position that we're looking for is percentiles. Percentiles are used in educational and health-related fields, and it indicates the position of an individual in a group. We've all heard that you're in the 98th percentile of your class, or your child is in the 75th percentile for their weight or their height, things of that nature. Well, how do we get those percentiles? Basically, we're taking everybody and breaking them up into 100 little parts. We're taking that and, like I said, breaking everybody up into 100 equal groups, and then based off of that, putting your child or yourself into one of those categories. In order to do that, we do use a formula, and we use that percentiles are equal to the number of values below the x. In other words, the number of values below whatever number you're at, plus 0.5. We always tack on a half. Then we're going to divide that by the total number of values that we have. This is like our n. How many do we have in all? And then multiply that by 100. So it's like a percent. Okay? So we take out how many things are below us, add on a half, and then divide by the total number that we have and multiply by 100. Let's look at an example of this and see exactly what we mean. So here we have a data set for test scores. We want to find the percentile rank for the test score of 47. So we want to find this percentile rank. Anytime we're looking at percentiles, we always want to put them in order from least to greatest first. Step one is always put them in order from least to greatest. So I'm going to come in here and I'm going to put them in order. I've got 12, 28, 35, 42, 47, 49, and 50. So I've put them in order from least to greatest. And again, we're looking for the percentile rank of 47. So then I'm going to see how many numbers are below 47. These are all below my x. This is my x value. Okay? So there are 4 numbers below. So percentile was the number of values below x, which is going to be 4, plus 0.5, divided by how many total there are. Well, there's 1, 2, 3, 4, 5, 6, 7 total numbers. So we're going to divide by 7 and multiply by 100. So I get 4.5 divided by 7 times 100. So I get 64.3. So the test score of 47 is in the 64th percentile. So again, we take out how many numbers are below it, divide by the total number, and multiply by 100. Do not forget to tack on this 1/2. It's very important because otherwise you can't account for the smallest number and the highest number. Percentiles you'll see most, again, in educational and health related fields, because it does break it up into 100 even parts, and like in education, so many things are based off of 100 points, and that's what we're used to. So we always think of 100%, and so we're always looking at those percentiles. Another type of position that we measure is looking at quartiles. Instead of percent and percentiles where we break it up into 100 parts, in quartiles we break it up into 4 even parts. And the divisions are designated by these Q1, Q2, and Q3. These are the breaks in between these quartiles. And Q1 represents the first 25%. The Q2 represents 50%. Q3 breaks off 75%. And what it looks like is here I have my lowest value, and over here I'm going to have my highest value. So over here we have the highest value. Okay. In the center is going to be Q2 because that breaks it up into 50-50. Then here is going to be Q1, and here is going to be Q3. So between the lowest value and Q1 there's going to be 25%, 1/4 of my line. So anything below this Q1 is 25%. Then from Q1 to Q2 is another 25%. Therefore anything below Q2 is going to be a total of 50%. From Q2 to Q3 is another 25%. So we're looking at from Q3 and below a total of 75%. Then we have the remaining 25%, so that we add up to an entire 100%. Again, we're breaking it up into 4 even parts. When we want to find these Q1, Q2, and Q3, we're going to be looking for the medians. Okay? Medians are going to play a big part here. But of course, the first thing that you always, again, want to make sure that you do is arrange the data in order from lowest to highest, least to greatest. Then you find the median of the entire data set. The median of the entire data set is Q2. It's the middle. Remember, that's what breaks it up into the 50-50. Then we're going to find the median of everything below Q2. And we have to be careful here. We do not include Q2 in the numbers that we're counting here. And I'll give us an example in a minute. But we don't include that number in there. Okay? Then to find Q3, we find the median of the values above Q2. So let's go to an example. I want to find Q1, Q2, and Q3 for the data set that has 15, 13, 6, 5, 12, 50, 22, and 18. Okay. Step number 1, always put them in order from least to greatest. So we have 5, 6, 12, 13, 15, 18, 22, and 50. Very important. Make sure you put them in order from least to greatest. Step 2, find the median of the entire data set. So if I'm looking at this entire data set, I have 8 numbers. So I'm looking for the middle number. Well, the middle number is going to be right here where I divide the numbers in half. So it's going to be right here. So I'm going to take Q2 is going to be equal to 13 plus 15 divided by 2. Remember, if there's not exactly a single number in the center, then I have to take the 2 middle numbers and divide it by 2. So I take 13 plus 15 and get 28 divided by 2. So my Q2 is equal to 14. That is my Q2. To find Q1, what I want to do is I want to take the median of the lower part of my numbers. I don't want to include my Q2. Well, Q2 was 14, so I'm not going to include it. I do want to include 13, even though I used it to find Q2. It is not actually Q2. So I'm going to use it still to find my Q1. So the middle of these lower numbers is going to be right here in between the 6 and the 12. So it's going to be right here. So Q1 is going to be 6 plus 12 divided by 2. So 6 plus 12 is 18 divided by 2, which is 9. I do the same thing for the upper portion, the upper half. Again, I'm including 15. I'm not going to include 14 because 14 is actually the Q2, but I will include the 15. So I'm going to look at 15, 18, 22, and 50 and get the middle number there, and it's going to be between 18 and 22. So between 18 and 22 is going to be Q3, and divide those by 2. So Q3 is 20. So I have my Q1, my Q2, and my Q3. Let's look at another data set so that we can see the difference in when we do use and we don't use Q2 to find the others. So if I give you the data set of, let's say, 1, 2, 5, 7, 9, 12, and 14. Okay, so in this one, step 1 is to find the middle number, or actually to put them in order from least to greatest, which I've actually already did. So step 1 is to find, put them in order from least to greatest, which it's done. Step 2 is to find the median. So of these numbers, there are 7 numbers, so the middle number is actually a single number, and that is 7. So Q2 is 7. Since my middle number, my median, my Q2, is actually a number in the data set, when I go to find Q1 and Q3, I no longer use this number. It's like it is gone. Okay? I use the numbers below that, or the numbers above that. I don't include the Q2. So I find the median of these numbers. And the median of the lower numbers is going to be 2. So my Q1 is 2. And the median of my upper numbers, which is Q3, is going to be 12. So in this case, I didn't use the number that was Q2. I didn't use it in the previous example either, but I had a little bit of a difference there. So hopefully that will help you understand when you do and don't use the actual middle numbers. Okay? And if you have questions, please let me know. We're going to continue with quartiles because there are a couple of other concepts that we use with quartiles. And one of them is what we call the interquartile range. The interquartile range, also referred to as the IQR, is the middle 50%. It includes everything from Q1 to Q3, and what it is what is the distance? It's the range from Q1 to Q3. And so the interquartile range is actually Q3 minus Q1. We actually take that difference and get a single number. So your IQR is actually that subtraction. We actually do the subtraction. Okay? And the reason why we do this is we use the IQR in order to look for outliers. Outliers are extremely high or extremely low data values when compared to the rest of the data set. These are things that can drastically change or affect your mean or your standard deviation. They're the things that really look a little bit off to you. Now I will say not all data sets have outliers. Some do, some don't. Some will have more than one outlier. It just depends on your data set. Some will have an outlier on both ends, and that's okay. We just want to be able to identify your outliers if you have any. So let's look at the steps for identifying your outliers. Again, step number 1, arrange the data in the order from least to highest, lowest to highest, least to greatest. And we want to find Q1, Q2, and Q3. That's our quartiles. Step 2, we want to find that inner quartile range, the IQR. We actually want to subtract, make sure we get a single number. Then we're going to multiply that IQR by 1.5. This gives us that buffer zone, gives us some buffering, gives us enough room on both sides to make sure that we don't miss anything, and so that we know that we are using outliers. Step 4 says that we subtract the value from step 3, which is 1.5 times IQR, from Q1. And what that is it's this formula right here, Q1 minus 1.5 times IQR. And then we add the value in step 3 to Q3. So we're actually going to get two different values. We're going to have an upper cutoff and a lower cutoff. Anything outside these cutoffs is going to be outliers. So let's look at what this actually looks like. We want to check the data set for outliers. Check this data set for outliers. Step 1. Put them in order from least to greatest. Least to greatest. 116, 118, 119, 122, 125, and 145. Okay, I've got them in order from least to greatest. Then I want to find my Q1, Q2, and Q3. Well, I've got an even number of data points, so my Q2 is going to be right here. It's going to be 119 plus 122 divided by 2. So Q2 is going to be 120.5. Q1 is going to be the median of all of these. So Q1 is 118. Notice I included the 119 because it is not exactly my Q2. I'm going to include my 122 because it is not exactly my Q2 again. So my Q3 is going to be 125. Unless a number is exactly your Q2, you include it when finding your Q1 and Q3. Now then, the IQR, that is equal to Q3 minus your Q1. So in our case, we have 125 minus 118. So our IQR, or our inner quartile range, is going to equal 7. We want to look at this data from the upper end and the lower end again. So we're going to look for a lower cutoff and an upper cutoff. The lower cutoff is Q1 minus 1.5 times the IQR. The upper cutoff is Q3. Notice I'm using the same numbers that are used in the IQR, Q1 and Q3, those outside quartiles, plus 1.5 times IQR. So let's see here. My Q1 was 118 minus 1.5, and my IQR was 7. So I've got 118 times, or I'm sorry, minus, and then 1.5 times 7 is 10.5. So 118 minus 10.5 is going to give me 107.5. That is going to be my lower cutoff bound to look for outliers. I do the same thing over here, except I use my Q3 and I add, because I'm looking for anything larger than that, 1.5 times 7, and I get 125 plus a 10.5, so that's going to be 135.5. So these are my two cutoff values. So let me rewrite the data set that we had. We had 116, 118, 119, 122, 125, and 145. Now I'm going to go back in here and identify that 118 was Q1, 125 was Q3. Okay? Then I'm going to place my lower and my upper cutoffs on the same area. So 107 would be about right here, 107.5, and 135.5 would be here. And I'm going to kind of box it in. Notice, one thing I want you to notice is that my cutoffs are above Q3 and below Q1. That's where they need to be, because I subtracted from Q1, making it below Q1, and I added to Q3, making it above Q3. They should be outside these two numbers. Any number in the data set that is not inside this box, inside these cutoff values, is considered an outlier. If there is a value outside this box, it is considered an outlier. $145 is an outlier for this data. Now for another data set, it may not be an outlier. It is for this data set. Anything outside that box. Again, some data sets may not have outliers. Some may have several outliers. You have to look at each individual data set. And some of them may look like they're outliers, and they may turn out to not be. And some of them may look like they're okay, but you got to check them in case. Do the math. Make sure that you do this procedure to verify your answer. This is considered the verification. You must do this. Show your work. Very important to make sure that you're showing your work. If you don't show your work, it's not worth the credit. If you have questions or need help, please let me know.